The Haber process. Today's lesson, we're going to cover the Haber process for the AQA students and then look at fertilizers. Now, the Haber process is used to make ammonia, NH3, and it's done by reacting nitrogen and hydrogen, which are the two elements present in the actual ammonia. Now, you need to know how to balance the equation, obviously. Everything is a gas, so G. And it is a reversible reaction. So as soon as the ammonia forms, it can break back down into forming nitrogen and hydrogen. You need to know how nitrogen is obtained. So nitrogen is 78% in the air. Obviously, you can't just grab the nitrogen. What you have to do is do a refractional distillation and cool down and condense the gas. Now, hydrogen, on the other hand, comes from natural gas methane. So that's how you obtain your hydrogen. Next, you need to know the conditions for these. So the conditions are pressure is 200 times greater than the room. So the room is 1 atmosphere. This is 200 atmosphere. The temperature is 450 degrees, and the catalyst is a solid iron metal. So you pass it over an iron metal. The process looks a bit like this. You feed hydrogen and nitrogen into the reactor. They react together and they form ammonia. Ammonia can then be tapped off as a liquid. And the N2 and H2 that have not reacted or have been kind of reformed because the reaction shifted backwards, they get recycled back into the reaction mixture. So the ammonia is actually formed by cooling the mixture of the three gases. Now, ammonia has the highest boiling point. So it will cool and condense first. The nitrogen and hydrogen get fed back into the system by recycling them. Now, in these questions, just like the equilibrium topic, you might have to explain the compromise bit a bit more. But ultimately, you need to know which way the equilibrium shifts. So from here, you can see that as the temperature is going up, the yield is going down. So that means the reaction is shifting left. And that's because, remember, the forward reaction is exothermic, so this should be a negative enthalpy change. So the forward is exo, the backward is endo. So if you increase temperature, it'll shift to the endothermic side. That's why the yield got less. So that means ideally, you need to have a very low temperature. So a low temperature would mean that the reaction will shift to the exothermic side, which is in fact the right side, which will make more ammonia. The problem is, and this kind of like rhymes, if the temperature is too low, the reaction is too slow. That's the way to remember it. And the reaction is too slow, there's no point to get a really high yield, but wait 5 days to get your first batch. Therefore, you have to reach a compromise. Similarly, with pressure, you can see as the pressure goes up, let's have a look. Yeah, as the pressure is going up, the yield keeps increasing, but it's kind of leveling off. So it's not making much difference if you keep increasing it. So if you look at Y, the left side has 4 moles, this side has 2 moles. So if you increase pressure, it shifts to the side with less moles of gas, which is the right, which makes more ammonia. Now, why can't the pressure be too high? Well, you could get an explosion because the equipment has to be very fancy and they could still explode and also be very costly to generate the high pressure and maintain the equipment. So again, you have a compromise between, in this case, yield and costs, and in this case, yield and rate. So be able to answer questions such as this. Now, a catalyst will speed up the rate of the actual reaction, but it will speed up the forward and backwards equally, so they'll cancel out. So have no effect on the equilibrium position. So why is it used? Well, it's used to lower the activation energy so that a lower temperature can actually be used for the reaction, which will save on energy and money. That's the purpose. These diagrams we talked about in the rates of reaction topic, so we don't need to revisit it now. It's showing you how the activation energy is smaller, the green one, for the reaction with the catalyst. And similarly, E5 is smaller than E4. These are some advantages in general of using a catalyst and some disadvantages that you should be aware of. And this is the final part of the ammonia bit. So advantages for using catalysts is because they can be reused because they're not used up. They increase productivity. They lower temperature use, so lowest temperatures can be used, which means less fossil fuels will be burned, which will generate less CO2. And less fossil fuels being used helps to kind of save on these limited finite resources. The disadvantage is the catalysts can be expensive. They're specific to their reactions. They don't work on all reactions. They can get poisoned, which means impurities can block their active sites and stop them working. And to actually get your catalyst out, you'll need to find a way to separate it and filter it out at the end. So that completes the Haber process. Next, we need to talk about fertilizers. So I'm going to use my PowerPoint here to introduce this part of the course. So I always start with this. Now you might say, why? Well, this is a bowl of cereal. Now cereal comes from wheat, and wheat comes from farming. And farming requires fertilizers to improve its productivity. So the lesson objective today is to learn how fertilizers are formed, why they're important, and write out their equations. The first question is, why do we need fertilizers? The answer is it will improve your farming by giving you a high yield. And also, humans keep increasing in population size, so there's a higher and higher demand for the crops. And lastly, land that can actually be used to grow the wheat is running out, so the land has to be reused. Okay, so each time a soil is used, it loses its nutrients over time and its minerals. So you need to add more artificially using fertilizers. That means 40 years ago, it was much nicer growing a tomato organically. Now they have to put extra fertilizers in. Now, the ones you need to know are called the NPK fertilizers. So NPK stands for nitrogen, phosphorus, and potassium. My face is a bit in the way there, so if I move it here. NPK fertilizers, which stands for nitrogen, P for phosphorus, and K for potassium. So remember, the P is not potassium, K is potassium. So these are essential minerals that the plant needs to grow. And obviously, if you do biology, you can learn more in detail what they do. For our chemistry purpose, we do not need that. Now, NPK fertilizers are actually called formulations. Remember, formulations are mixtures that are made to have specific proportions. So, for example, a farmer might want to have more phosphorus, so he might choose a ratio of 10 to 30 to 10, or 1 to 3 to 1. So that's an important point, that they're formulations. It links back to the beginning of the course. Now, when ammonia is produced in the Haber process, 10% of it actually gets converted to nitric acid and then re-reacted with ammonia, because that makes one of the most important fertilizers, ammonium nitrate. So let's have a look here. Ammonia fertilizers are produced when ammonia has to react with an acid. So it's always ammonia plus an acid. You can obviously use any of the 3 acids or 4 acids that you know. But one of the most important is this one. Ammonia plus nitric acid makes ammonium nitrate, NH4NO3. It is a neutralization reaction because it is between an acid and a base. Now, this is the reason that from the Haber process, we use NH3 first to make nitric acid, so then we can react it with ammonia, because by making ammonium nitrate, we make a very high percentage mass nitrogen. Is the highest percentage mass by nitrogen in its compound compared to the other fertilizers. So you get the biggest bang for your buck in terms of nitrogen. Now, can you guess how to form ammonium sulfate or ammonium phosphate fertilizers? Well, obviously you have to use the correct acid. In this case, sulfuric acid for the sulfate one and phosphoric acid for the phosphate one. That part's easy. The hard bit is writing the balanced equation. So in order to do that, you need to know the table of charges. So before we move on, we must look at the following. Okay, these. So these are the four acids that you should know. HCl, HNO3, H2SO4. That you must have seen before. This might be the new one. Phosphoric acid is H3PO4. Now, each one forms a different salt. This is from the acids and bases topic and salts. But you should know that hydrochloric acid makes chloride. Then all the other ones end on ate because they have oxygen. So we have nitrate, sulfate, phosphate. You also need to memorize the ions with their charges. So NO3 minus, SO4 minus, and PO4 minus. That will help you form the equations. So I should have them written out. One second. We should have some equations here. No? Okay, we can write a few equations actually out just for practice right now. So we can have NH3, the other two possibilities, plus H2SO4. And we can have NH3 plus H3PO4. Now, NH3 is ammonia and it forms the NH+1 ion. So when that combines with SO4 minus, you need two of these plus ones to balance the -2 charge. So it will be NH4 twice SO4 as the product, which means you'll need a 2 here to balance everything out. And for this one, it'll be NH4, NH4 3 times because PO4 is 3 minus. So we need 3 plus 1s to cancel it. So you need 3 here to balance it. Okay, so everything is AQ. All the state symbols will be AQ. We don't use ammonia gas. We use ammonia when it's ammonia solution. So this particular fertilizers will contain nitrogen and phosphorus. This one will contain just nitrogen. And we still haven't done the potassium one. Okay, but these are 3 different possibilities. So you can have ammonium phosphate, ammonium sulfate, or ammonium nitrate, which all contain nitrogen. And obviously this one also contains phosphorus. Now, how to actually make the fertilizers? So go back here. So nitrogen, we already talked about how to get a fertilizer with nitrogen. You take your ammonia and you react it with nitric acid and you form ammonium nitrate. Or you can use the other acids. Now, for the phosphorus one, as well as having the ammonium phosphate, what you do is you mine some phosphate rocks and then you react them with acids to make fertilizers. And this is the bit that requires, I would say, quite a bit of memory, okay? The potassium one is very easy, actually, because potassium salts tend to be soluble in water. So the rocks, you mine them from the ground, such as potassium chloride or potassium sulfate. Then you just put water on them. And because they're water soluble, you'll form a solution of, say, potassium chloride, which will have the potassium bit that you want for your fertilizer. So those are the more simple ones. Now, the harder ones are the phosphorus ones. So remember, the phosphorus one is insoluble in water, so it cannot be treated directly with water. It has to be reacted with an acid. And there are different product outcomes for each. For the potassium one, you can just dig it up from the ground and add water to it. So if we have a look here, now I always need to kind of remind myself of this even every year because the products don't always seem very obvious. What you have to understand is that all these rocks contain calcium, and that's why you see calcium there. So you need to know what happens when phosphate rocks react with any of the 3 acids. If we start with nitric acid and the phosphate rock, it forms 2 things. calcium nitrate, because the calcium was in the rock, and also phosphoric acid. That's the bit that might be a bit like, oh, why is that there? Well, it just is. That's what it forms. You don't need to write balanced equations for these. You just need to know it in words. Now, the phosphate rock reacting with sulfuric acid makes calcium sulfate and calcium phosphate. And the final one, phosphate rock with phosphoric acid down the bottom, has only one product, luckily. It's called calcium phosphate, and it's sometimes called a triple superphosphate. And the reason for that is that the formula is Ca3PO4 twice. I will show you this. I mean, that's it for the course on this. However, I'll show it to you in the table format, and I'll recommend learning it. And I'll help you do that with a few suggestions. But this ultimately is the table that you need to have in your head. So if we start again, this is the rock being treated with each acid. So with nitric acid, it makes calcium nitrate and phosphoric acid. Then you could even take your phosphoric acid and react it with ammonia to make ammonium phosphate. Then that'll be a nice fertilizer that contains nitrogen and phosphorus. Now, you could form, with sulfuric acid, the phosphate rocks makes calcium phosphate and calcium sulfate, called a superphosphate, because of this Ca3. And the phosphoric acid with the phosphate rock just makes calcium phosphate, which we call sometimes a tricalcium phosphate, because obviously it's Ca3. Don't worry about these names in bold. What you need to know is these two products, and this one product. So if anyone asks you what happens if I add phosphoric acid to a phosphate rock, you can just say it forms calcium phosphate. The way I recommend, and I will attach this to your notes so you can practice it, is these boot camp quizzes, which are just generic questions that you should know by heart for the Haber process and for the fertilizers. So it's a good summary to test yourself if you know if you learned well from my lesson or from your notes. You should know the answers to all of these. So N2 plus 3H2 makes 2NH3, 450 degrees, 200 atmospheres, shift to the left, shift to the right, iron, lowers the activation energy, increases rate of reaction from the air, from natural gas, cool and condense, recycle. Know your answers straight away. For the fertilizers, you need to know these questions. So ammonium nitrate, nitrogen, phosphorus, potassium. Any fertilizer which contains potassium will be one that you put water on the rock, the potassium chloride rock. Ammonium phosphate would work. Ammonia plus nitric acid. From mining rocks from the ground that contain potassium chloride and dissolving in water. Insoluble in water. And these are the ones we just did. Okay, so calcium nitrate and phosphoric acid, calcium sulfate and calcium phosphate, and then just calcium phosphate. These 3 points. So practice this, and it's a good way to see if you've learned everything. And that is the end of the course on equilibrium. So I will see you next time. Thank you.